To find the surface area, if a smooth parametric surface S is given by the equation, and so here we have our vector equation, r in terms of uv, x of uv plus y of uv plus z of uv, I, j, and k components, where uv is in our domain. And S is covered just once as uv ranges throughout the parameter domain D, then the surface area of S is, A of S is equal to the double integral of the distance of magnitude RU cross RV dA, where RU is pretty much the partial derivative of our vector equation with respect to u, and r sub v is also the partial derivative of our vector equation in terms of, or with respect to v. So find the area of the surface. The part of the plane with the vector equation r of uv is equal to u plus v, 2 minus 3u, and 1 plus u minus v. That is given by z 0 is less than or equal to u is less than or equal to 2, and negative 1 is less than or equal to v is less than or equal to 1. Alright, so we just want to find the area of the surface, which is not going to be complicated. All we need is that formula, and so we're just going to go ahead and substitute in the formula. We find r sub u, so we're just taking the partial derivatives of our vector function with respect to u. We get 1, negative 3, and 1, and do the same thing with r sub v, but with respect to v, we get 1, 0, negative 1. And then we're going to take the cross between the two, r sub u cross r sub v, and that's going to be equal to 3, 2, and 3. After we've done that, now we're going to find the area of our surface area. And so we take the double integral. Again, you could have, if you wanted to, it doesn't have to be, d, v, our v terms on the inside, our u terms could be on the inside, right? So that, didn't matter. I'm going to go ahead and, integrate on the inside. So we get 0 to 2, or integral from 0 to 2, integral from negative 1 to 1, square root of 22, dv du. Again, that just comes from square root of 3 squared plus 2 squared plus 3 squared. 9 plus 4 plus 9 is square root of 22. So that's how I get the square root of 22. Alright, dv du, just put the square root of 22 on the outside because it's a constant. 0 to 2 du, and then negative 1 to 1. Go ahead and find the area there. So the square root of 22 is just 2 minus 0. And then 1 minus negative 1, so it's going to be 2 times 2, which is 4, so 4 squared is 22. I'm just going to go ahead and do the last page as well, because it's not going to take too long. Alright, so surface area of the graph of a function. So for the special case of a surface S with the equation z equals f of xy, the parametric equations are x equals x, y equals y, and z equals f of xy. Kind of something I already told you. Depends on, what type of, on what region that we're doing. I mean, if I decided to do it about the, I'm trying to think of the other one that we haven't used yet, because we did xz, so, not yz. So if we did yz plane, if we were doing the yz plane, then all that would be is that, well, x would be a function of y and z. Y would equal y, and z would equal z. Alright, so that's all that's kind of saying. That's kind of special. Alright, our surface area is just going to be, then we can make it look a little bit easier for doing it to one of our planes. It's just the square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared. Again, this is if we're doing about the xy plane. And again, that should look familiar from Calc 2 when we're talking about arc length, where the arc length is just the integral from a to b, the square root of 1 plus the derivative of y with respect to x squared, dx. Alright, so find the area of the surface. So part of the surface S, so part of the surface z equals 1 plus 3x plus 2y squared that lies above the triangle with vertices 0, 0, 0, 1, and 2, 1. Alright, so what we are going to have is that x is equal to x, y is equal to y, and z is our function, so z is equal to f of x, y. And so in order to go ahead and plug it in, what I'm going to do is I'm going to do the partials first. So I take the partial of z with respect to x. So z, again, is that equation. Derivative of that with respect to x is just 3. Derivative of 2y squared with respect to y is just 4y. That kind of leads us into a little bit of complications, and the reason that gives us a little bit of complications is because now instead of just dealing with constants, when we have our integral, we actually have a variable. So that kind of dictates what, how we're going to set up our integration. So here you see that this line right here, the diagonal, there's two ways to write it. Y is equal to 1/2 x, or x is equal to 2y. If I went ahead and said, let's use x's on the outside instead of y. So here you see the x's are on the inside, y's are on the out. It's going to be a much more difficult integration if I decided to use, the y's on the inside as opposed to the x's. But because I'm using the x's on the inside, all right, that tells me that I should use x is equal to 2y as my top component for my integral. Oops, I went a little too far. I don't know what I deleted there. So we're going to use x is equal to 2y and put x's on the inside. That way, when I do the integration of the inside, it's just x, and it makes it work a lot easier. All right. And so that's why I went ahead and make x the inside, and that's why I went ahead and made sure that I use x equals 2y as my upper limit for the inside integration. So take the antiderivative of that and just get x squared to 10 plus 16y squared. Substitute in the 2y and 0. I'm going to get 2y squared root of 10 plus 16y squared. When you substitute in 0, it's just going to be 0. Now integrate that. I'm going to get 1 over 24 plus 10 plus 16y squared, 3/2. 0 to 1, that's just use substitution. Substitute in the 1, and then substitute in the 0. I'm going to get 1/24 is 26 to 3/2 minus 10 to the 3/2.